Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and in this video, I'm going to talk about analyzing an op-amp circuit and also talk about finding the frequency response at a particular value. This one's quite a bit different than anything else we've already seen, but we still follow our same steps. We assume that the currents going into the terminals are equal to 0. We assume that V plus and V minus are equal since we have negative feedback. So let's put in some values this time. So we'll let R1 be 3K, and that appears in two locations. R2 is 50K, and of course these are in ohms. And the capacitor is 120 nanofarads. And nano, of course, is 10 to the minus ninth. And we want to find the gain V out over V in. So here's our circuit, just redrawn. So we have INs are both 0. We have V plus is equal to V minus. And now we need to do nodal analysis at those two terminals into the op amp. So I've marked them with red dots. At the top dot, we can ask what is the current through the 3K ohm resistor, and we know that that current is 0. And the reason that current is 0 is the current here is 0, right? So I could have written an equation and I would have solved it, and it would have been, it would have told me that Vn is equal to V plus. We do know, by the way, that if the current through that resistor is 0, there's no voltage drop across it, and that will make V plus equal to Vn. But suppose for a moment that we didn't know that, and we just wanted to write an equation. We would write V plus minus Vn over 3K, 3000, plus 0 is equal to 0. Okay, so we have this current going here, V plus minus Vn over 3000, and this current here, which we know to be 0. When we solve for that, we'll end up with V plus is equal to Vn. Okay, so you can either know that V plus is equal to Vn because this current is 0, or you can go ahead and calculate it if that works for you. So but the end result is the same. V plus is equal to Vn. So now we can write the nodal equation at this node here, and we end up with V minus V out over R2. Okay, so that's V minus V out over R2 plus V minus 0 over R1 plus 1 over SC. That's this current here. And then we add this current here, which is 0, and that's equal to 0. So now we can go ahead and manipulate this. Remember, of course, that V minus is equal to V plus, which is equal to Vn. And we end up with this equation by just making that substitution. So the next thing we do is we want to clear the denominator here. So we multiply 3 by SC over SC. That gives us SCVN over SCR1 plus 1. I didn't change this term. And then the next thing we do is we factor out the Vn and factor out the V out and move it to the right. And that gives us a very messy expression when we find V out over Vn. But we can go ahead and take this part, multiply it by R2 because of that side, and we get SCR2 over 1 plus SCR1 plus 1, and then we can just multiply this one by 1 plus SCR1 over 1 plus SCR1, and we end up with this term. So now if we plug in all the values that I had before, we'll actually end up with this value here. Okay. Now if you wanted to, instead of keeping track of things in terms of R1 and C and R2, you could have plugged in the values right ahead. It's kind of a matter of preference which you prefer to do. So here's our frequency, our transfer function. So we can get the frequency response from MATLAB, and we see it's kind of strange, and it has actually no practical value. So this is just a circuit that I created so that you could analyze a circuit. Another thing that sometimes students want to know is how they could find out the frequency at the magnitude and the phase angle at a particular frequency from the transfer function. Of course, we can read it from the graph, but let's see what happens. Let's consider omega is equal to 10 to the third, which is 1,000. Okay, so what is the magnitude of the transfer function g at 10 to the 1,000? Sorry, at 1,000 radians per second. So what we do is we plug in J1000 in terms of S, right? Remember, we can say S is equal to J omega. So we plug in J1000 and we end up with this expression here. Multiplying things out, we get a complex number divided by another complex number. I use MATLAB, you could use your calculator. And there it is, written as an exponential form number. From this, it's easy to see that the magnitude is 6.0144, and the angle is 1.0353. Okay, we can put that in degrees by multiplying by 180 over pi, which is about 59 degrees. Now, if we look at our frequency response that I've blown up here, let's look at what happens at 10,000, I'm sorry, 1,000. Is going to be there. Okay, I could read to the right side or to the left side. I usually choose the closest side. And if we look at that, we have this is, let's see what it is. This is 10 to the 0. I can write them on this side for my convenience. 10 to the 0, 10 to the 1, 10 squared. So now when I read this is 10 to the 0, which is 1, 2, 3, 4, 5, 6. So that means at omega is 1,000 radians per second. The magnitude of G is 6, about, from reading, which is what I'll put a squiggly, which is about what we had before. And if I look at the angle, okay, now this one is semi-log. So on the side we have 0, 20, 40, 60, 80. I'm just copying from the other side so I can read, and it looks like it's about 60 degrees. Okay, if I were looking more closely, I might see that actually I'm a little bit off there, but it's going to be close to 60 degrees. And when I look at this, in fact, that's what I got, was 59-ish. So reading from the graph is notably less reliable just because of your eye. If you were using MATLAB, you'd be able to read it more closely. But so sometimes I might ask you to read from a graph. That helps me to make sure you understand how the graph works. And sometimes you can always, if I give you the transfer function, you can check yourself with that as well.